All right, 2016 number 2. This should be a 15-minute long one for us. I've actually, if you look on the College Board, I've actually cut off the last question. The last question is a little weak acid question, and so you don't have to worry about it. So I chopped it for us. So we're just parts 1 through or A through E. It says student makes an experiment. They have NaHCO3, sodium hydrogen carbonate, it's baking soda, and acetic acid. The reaction is represented by the equation above. Student places 2 grams of baking soda in 60 mils of 0.875 molar acetic acid. They observe bubbles. Their flask gets cooler. That means that this reaction is endo or exothermic. Good, it's endothermic. So the delta H is on this side. That's good for you to understand for equilibrium shifts. It says, identify the reaction represented above as acid-base, precipitation, or redox. You could do it either way. You could either say it's an acid-base reaction because the acetic acid, that weak acid, is donating a hydrogen over to the sodium hydrogen carbonate to make that carbonic acid that's decomposing. That's fine. Or you can justify this by saying why it's not one of the other two. So you can say this is not a precipitate reaction because there's no solid produced on the product side. You can say this is not a redox reaction because there's no change in oxidation numbers. So you either have to say why it's not these or why it is these. I think the not is lots of times easier here to eliminate those than to justify that acid-base reaction, but either way is good. Good. B says, based on the information above, identify the limiting reactant. Justify your answer with a calculation. So we've got to figure out which one of these is limiting. We've got grams of NaHCO3 will turn into moles. We've got molarity and volume of the acetic acid. So we have moles of that, and then we can compare those moles. It happens to be a 1-to-1 ratio, which is nice for us. So here we go. I'm going to do, on part B, I'm going to do the 2.24 grams first. 2.24 grams of NaHCO3. Turn them into moles. 1 mole of that is 84 grams, and that gives us the moles of sodium hydrogen carbonate, 0.0267 moles NaHCO3. Then I'm going to turn the other one. The other one gives us 0.875 molar acetic acid. And I'm going to multiply it by its volume in liters, 0.06 liters. And that will give us, that this thing is 0.0525 moles of acetic acid. That's the calculation part, and then somewhere you need to tell them which one's the limiting. Sodium hydrogen carbonate is limiting. Because the mole ratio is 1-to-1, and there are fewer moles of the baking soda. It matters that in that equation here it's a 1-to-1 ratio, or else we'd have to do a little extra math, but we don't here. So there's your calculation, there's your justification sentence, kind of sitting on part B. That's it for part B. Identify the limiting reactant. It says the student observes that the bubbling is rapid at the beginning of the reaction and gradually slows as the reaction continues. They're working a little kinetics in here. Explain this change in the reaction rate in terms of collisions between reactant particles. So part C, get this in here where you can see it. As the reaction proceeds, the concentration of the reactants decreases. So there will be fewer and fewer reactant collisions. And the rate will decrease. I'm hoping you can see all this. There's a wicked shadow right now. I'm like sun blind from the sun coming through the window. So there's part C. That's it on part C. Part D says, in thermodynamic terms, a reaction can be driven by enthalpy, entropy, or both. Considering the flask gets cooler as the reaction proceeds, that means it's endothermic. What drives the chemical reaction? Answer by drawing a circle around one of the choices. That's easy enough. Then it asks you to justify it in terms of delta G. So the favored thing is exothermic. So they favor it. This one is, the enthalpy is not favored, and greater disorder. When we look back up here at this equation, we have solid and aqueous things going towards aqueous liquid gas things. 0 moles of gas going to 1 mole of gas in the equation tells us that this guy is going to be driven by entropy only. Greater disorder in this guy, it's endothermic, which is anti-spontaneity as far as the enthalpy goes. Justify your selection in part D in terms of delta G. I wrote it this way. Write the equation. Delta G equals delta H minus T delta S. And then say enthalpy is positive and entropy, the disorder, is positive. In order to have a negative delta G and a spontaneous reaction, the entropy must be the driving force. So I wrote it. Enthalpy is positive, entropy is also positive. In order to have a negative delta G in a spontaneous reaction, the entropy must be the driving force. That's part D. Good. Part E gives us like a wicked description of how to draw up this hydrogen carbonate ion. It says the hydrogen carbon ion has 3 carbon to oxygen bonds. 2 of the carbon to oxygen bonds have the same length. The third has a longer length than the other 2. The hydrogen atom is bonded to one of the oxygen atoms. In the box below, draw a Lewis dot structure for the diagram or diagrams of HCO3 negative that's consistent with the given information. Alright, I've told you before, they don't usually say diagrams when it's not resonance. So this one is a resonance structure. It's a good indicator it's going to be more than one drawing when you've got a big long box like this. Usually they just give you a box half that size if there's only one structure. So it tells us here hydrogen is bonded to one of the oxygens hydrogen bonded to one of the oxygens. And then we've got our carbon. Two of the three, all three oxygens are bonded to the carbon, so our structure is going to look like this. It's an ion. You've got to put this thing in brackets. It has a -1 charge, and then I think it is extremely healthy to count electrons here. So we've got 6 valence electrons for each of the oxygens. That's 18 plus 4 from carbon, that's 22, plus 1 from hydrogen is 23, plus 1 more from the overall, that's 24 electrons, or 12 pairs that we're dealing with. I think that's worth making note somewhere, that's 12 pairs. We got 1, 2, 3, 4, fill in the rest. There's 5, 6, 7, 8, 9, 10, 11, 12 to take care of all those elements. What is our problem with this thing? Good catch. Yeah, our problem with this thing is that this carbon is short electrons. Carbon has to have an octet of electrons, and it doesn't here. It only has 6. And so we've got to pull a pair of electrons and make a double bond to that carbon. This, I've told you before, that hydrogen to oxygen to whatever the other element is, you got to leave alone. The pair doesn't come from this. The pair's got to come from one of these. Which one? It's arbitrary. It doesn't matter. And so we're gonna scratch one of those out. You should have a eraser on yours. Scratch one of those out and create a double bond on one of these. Good. How did I choose this one? It was arbitrary, which means that this is a resonance structure. And so we also have a situation where it looks like this. Where that's the other structure. Make sure you get brackets and a charge on it. So there's our other structure. Yes? This is why one of the oxygens, it says 2 of the carbon-oxygen bonds have the same length. It's these two are the same length. That has a bond order of 1.5. And one of them has one that's longer. That's this one. On both these structures, that's the longer carbon-to-oxygen bond. This has a bond order of 1. These have a bond order of 1.5. So bigger bond order here means shorter bond length, smaller bond order, longer bond length, but it's a resonance structure. It looks like that. So you may look back through that, count the electrons up, trust the training, right? Put the brackets around the things, hydrogen to oxygen to the rest of the stuff, and then just be careful because this one's a resonance. Okay, that's number 2 on 2016.